This is the Argmin video channel, the worst math videos on YouTube. On real analysis, lecture 21, compactness, the extreme value theorem, and uniform continuity. So, last lecture, if you recall, we looked at a lot of properties of continuous functions, particularly if A is a subset of Rn, and if A maps A to Rm is continuous. If you have a sequence in A and that sequence converges to point A in the set A, then this would imply that if you pass each of those points in the sequence to F, that sequence formed by that is also going to be converging to F of A. Okay, now our next topic is going to be on compactness and continuity. So, if you remember what compact means, it just means every that has a subsequence which converges in the set. So let's prove something about that. If C subset of Rn is compact and F maps C to Rm is continuous, then the image F of C, or the range, is compact itself. So let's prove that. Proof. Let there be a sequence in F of C for every k in the natural numbers. There must be some ck in C such that F of ck is equal to ak. Okay? Since those ck's are contained in C and C is compact, the sequence ck has a convergent subsequence which, let's say, converges to small c in the set big C. Since F is continuous, then if you pass everything in that subsequence through F, it should converge as follows. So AK of L goes to F of C. In FC. So F of C has a convergent subsequence as well and is compact. Alright, now this is the extreme value theorem. I tried to say that in my most extreme voice possible, but nonetheless, that probably didn't work. So here it is. If C contained in Rn is compact, and F map C to R, and that's continuous, then there must be some A, B, and C such that f of A is less than or equal to f of x and is less than or equal to f of b for all x in that domain. Okay, so let's prove this. I'm going to start writing smaller. So suppose that is compact and F mapping C to R is continuous by the previous proposition. We have that F of C subset of R is itself compact. So by Heine-Borel theorem, since it's compact, it is also closed and bounded. Okay. So we've used that prop. Now let's try to bring it to the end. Let's make an A and B and satisfy that. Since f of C is bounded, there must be some lower bound of f of C and some upper bound particularly the greatest lower bound and the least upper bound, the inf and the sup respectively. Since M and M are in the closure, just by a property, you must have, and we can't say anything yet, and since this is closed, the closure must equal the set itself. So let M equal f of A and M equal f of B for some A, B, and C. So for all x in C, it has lower bound f of A less than or equal to f of x and upper bound f of B. Okay. Now an example, take a function f from Rn to R defined as f of x is equal to -1/1 plus the norm of x squared. We can show that f is continuous if x goes to v, then f of x will go to -1/1 plus norm b squared. And the norm is a continuous function, so all of this works. Okay. Then this is primum of f on the set Rn is equal to 0, but there is no such v in Rn that satisfies -1/1 plus norm of v squared. And why? Because Rn is not compact. This little example will just remind you of that fact. So the extreme value theorem does not hold. The domain has to be compact for this to hold. Rn is complete, but not compact. Okay, now let's talk about uniform continuity. Let me write for you in pretty cursive. Continuity. Oop. Definition: a function f mapping a to Rm such that a is contained in Rn is uniformly continuous if for all epsilon greater than 0 there is a delta greater than 0 such that norm of fa minus f of b is less than epsilon whenever ab is in a and a minus b is less than delta. So one thing to note is this delta is only dependent on epsilon now and is not dependent on a. So it has to hold for every a and a. One remark after I highlight this. If it's really bad. Remark. F is continuous at a in a, then for all epsilon greater than 0, there exists a delta based on a and epsilon greater than 0. So a here is fixed. X in a, x minus a less than delta implies f of x minus f of a is less than epsilon. Okay, example. Let's take a function from the real numbers to the real numbers, defined as x squared. So, is it uniformly continuous? We know it's continuous, just because we've seen it a lot, probably, in previous classes. It's not uniformly continuous. Let's show why. So continuity doesn't always mean uniform continuity. In this example, we'll show that. Suppose f is uniformly continuous, and we'll show that for epsilon equals 1, it won't satisfy the definition, so there must exist a delta on a delta, just a delta, greater than 0, not greater than theta, such that a minus b less than delta. It implies that a squared minus b squared, that's just f of x minus f of b, is less than epsilon is equal to 1 for all AB in R. Now we'll end up with let's construct a sequence and show that it's not uniformly continuous. So let's take n plus 1 over n and n. So we construct AB such that A minus B are less than delta. They're very close. And then if you take n plus 1 over n minus n, that's just the same as 1 over n, which converges to 0. Now if we fix n such that n 1 over n, is less than delta, then we have that n plus 1 over n minus n is equal to 1 over n is less than delta. By our previous assumption, it must be that n plus 1 over n. Oh, and it's not clear. This is going to be A, and this is, I'll put it up top where there's space, B. And you pass that through the F, so square it, and pass that through F. We have that n plus 1 over n squared minus n squared is equal to 2 plus 1 over n squared is greater than 1. A contradiction with this being always less than epsilon equals 1. A contradiction. So F is not uniformly continuous. Okay, so x squared isn't uniformly continuous when the domain are the real numbers, but we'll see that if the domain is just a closed interval, it will be uniformly continuous. So let's just tweak it a bit. So instead of R, it's the closed interval from A to B. And if f of x is equal to x squared, and without loss of generality, let's just say they're both positive, formally continuous. Proof. Let epsilon greater than 0 be given, and choose some delta is equal to epsilon over, or we don't know this yet, but a little peek behind the curtain, it looks sort of like that. We'll fill this in later. Now let's pick something in the interval in the domain, and x minus y less than delta. Then if we do f of x minus f of y, substitute everything in through a definition of f, and that's just x squared minus y squared if we assume x greater than y, which we can do without loss of generality. And it's a difference of squares, so you remember some grade 10 math and do that, assuming you studied the same grade 10 math I did. I'm not going to make that assumption. Who knows what you know? You're just on YouTube. So that's less than or equal to x minus y times 2b. And so let's choose delta equals, let's see, one of the things to cancel out, so epsilon over 2b. So that gives us less than delta 2b. That's equal to epsilon over 2b times 2b, giving us epsilon. So F is uniformly continuous. And that caps it off for this lecture. We introduced compactness and uniform continuity. We're going to connect those ideas later on in this course. That's it. Thanks for watching. Put comments down below if you have any questions or anything else other than questions. And like and subscribe if you're on this video right now. I need a halt. Thanks.